Today we're going to take a look at section 11.2, which is vectors in space. And to start with, we're going to take a look at some, I don't have it with me, okay, it's some three-dimensional sort of ideas, okay? So we are going to extend our ideas from 2 dimensions, that's space R2, to 3 dimensions, that's R3. We specify each point by x, y, z. Your book, specifically defines a lot of things that I'm going to skim over. The reason I am is because we'll just do them as we do a part of the as we do the problems that we're doing. Everything is as you expect it to be. All right. So as you're looking at this and you're like, I already know how to do that. I already know how to do that. It just extends very naturally into 3 space from 2 space. So let me show you the part maybe that's a little bit weird, which is the graphing part. And I'm not going to promise that I'm good at graphing in 3 dimensions, but I'm going to show you how it looks. And you don't need a grid paper. In fact, it probably would be unhelpful to use a grid paper for this, okay? So we're going to plot the point. And the one that we're going to take a look at for our example is the point 3, 1, -5. So you're going to have your axis that's vertical, and then you're going to draw your other 2 axes down here like this. Okay? Our vertical axis is going to be our z-axis. That's probably different. Is it the same in physics? Yes. Okay, good. We usually do this one as x and this one as y. Yeah? Oh, good. There's every now and then there's things that we do differently, so this one looks like it's the same. So if you were going on the positive side of x, which we are, we're going to count this direction. If we were doing the negative part of x, we would go in the backwards direction over here, right? Does everybody make sense of that? So I don't want to draw in, these are the negative axes. That's where they are, basically. But if you draw in too much stuff, it makes it really confusing to look at. So we tend to draw just the positive axis on there. And then if we need the negative, then we'll draw it in. So I've moved 3 in the x direction. I need to move 1 in the y direction, but it needs to be done in such a way that I'm parallel to the y-axis. So if you think about coming out this direction, we're going to come out this direction too. So if I were to count on the y-axis over here by 2, it's going to look kind of like it forms this parallelogram right here with it, like that, and that would be where my point's located for now. So right now, I'm roughly speaking here. But then I need to use the z-axis. Oh, it was 1. Yeah, you're right. My bad. Thank you. And then I need to use the z-axis, and I need to go down 5 because it's -5. So I'm going to count down literally 5 from where my point currently is located, and that's going to be my location. So if you think about drawing, you're just going to, I didn't mean to do that one. This one I meant to do. Really. You're going to go straight down from here 5. So roughly, you're going to count it out. So you're going to go 1, 2, 3, 4, 5, and this is where we're going to plot it. Now I'm going to give some dimension to what we're doing here in just a second, because this is really still, it just looks like there's a dot in the middle of my paper, right? It really does. So what could we do to make it actually look a little bit more clear? So let me take a look with you at how we could do that. I don't want to do that. I want to erase my dots. So if you would imagine that what we did is we actually, I'll use that dotted line I did before, we actually drew this kind of a parallelogram. It's not perfect, but roughly speaking, right? Here's my parallelogram, just pretend. And then I went down 5 to get to here, but I could have gone down the same 5 to get to over here, the same 5 to get to over here, and if I connect these, what shape do you see roughly? This is terrible because my lengths are not quite right, but what shape are you seeing drawn? If I keep filling in the details. It's a rectangular prism, right? I see a 3-dimensional rectangle, basically. And that helps us to see how far we've gone down. And if you imagine, like you can almost see like there's a box lying below the XY plane at this point, okay? So if you can draw some dotted perspective in there, those of you who are artists, that'll be amazing. And those of you who are not, just do your best. Then it'll help us to do that. And you're not going to draw a whole bunch, all right? I'm not asking for you to draw a lot. I think there's 2 problems on graphing that each maybe have a couple of points you graph or something like that. And then you have, look, 1 in WebAssign, okay? But this is how it would look. Okay, so I mentioned that most of what we're doing is going to look like what you would expect, but we're just going to add a 3rd dimension to it. And so to give you some kind of a reference, or to give you an example of that, we're going to actually start with the distance formula. So we're going to find the distance between the points. And the 2 points that we're going to use are going to be 2, 1, 2 and 5, 5, 2. So if you're finding the distance between 2 points, what would that look like? You'd have a square root, and then you'd have, Ethan?
I believe we're dealing with total x squared plus y, total y squared plus total z squared.
Yeah. And so I think what we want is we want the difference in the x's squared, the difference in the y squared, and then the difference in the z squares. So everything just added that 3rd component of z in there. That's all it did. So if you take a look at the distance between the x values from 2 to 5, how far apart are they? 3. So as I'm working, I'm going to just simplify that as I go. So I mean, you guys are math people, right? So you know what's going on. How about the difference, the distance between the y values?
4.
That's 4. And then the distance between the z values?
0.
This one happens to be 0. Most of the time, of course, that's not the case. If we simplify 3 squared plus 4 squared and we add them together, what do we get? 25, and then square rooted would give us 5, right? Okay, so distance formula is just like you would expect, 3rd component z squared at the end. Good enough? Cool. An application of this is that we could actually talk about a triangle in 3 dimensions. And so what we're going to do next is consider a triangle. With the following vertices. We're going to find the lengths of the sides. And we're going to classify as a right triangle and isosceles triangle, which it could be both, right? Or neither. So it's either one or the other, both or neither. And our sides that, or our points that were given are going to be -1, 0, -2, -1, 5, 2, and -3, -1, 1. And I'm trying to be consistent with how your notation is in your book within the problems themselves. This is what it's going to look like. But it would be far easier if we actually gave these points names so that we can classify which ones we're doing at a time to find the distances. So I'm going to call this first point A, the second one B, and the third one C. You guys good with that? So what we need to do is we need to find 3 side lengths. And so that allows me to actually label that I'm finding side AB or AC or AC. So AB, and I'm going to use the distance formula. So what do we have for these lengths? What are my 3 values that are squared? I'll do the first one, 0 squared. What's next? 5 squared and 4 squared, but not the game 4 square. All right, so 5 squared plus 4 squared would be No, you can't square them individually. 25 and 16. 41, sorry. Yeah, we got 41. Cool. Okay. That's AB. How about BC? What are my three values to be squared here? 2 and 6 and 1. And if we square and add those together, what do we get? It's another 41, which means at the very least, this is what kind of triangle? It is isosceles, for sure, okay? Let's find out what AC is. What are my three values squared for AC? 2? And 1? I have 3 on the last one. Is it 3?
It's 3.
Okay. Okay, just checking. I make errors all the time, so it's certainly a possibility. All right, if I add those together, what do we get? 14. Okay, so how would I decide? We already know this is isosceles, and it's also not equilateral, but how would I decide if this is a right triangle? What would have to be true? Yeah, if 2 of them squared equal the third. And why can you why can you look at this and know that, Kyle? Okay, so if it's isosceles and it's a right triangle, then the isosceles sides would have to be the sides of the triangle and not the hypotenuse, right? You guys with me on that? And so the hypotenuse would have to be larger than that, and that would have to be, by the process of elimination, the square root of 14, so that can't work because 14 is smaller than 41. Y'all with that? Okay, so what we know is that this is an isosceles triangle. Only. Good stuff? Okay, we got the distance formula down. Do you remember in algebra, when you learn the distance formula, what for some reason is always the other formula you learn at the same time? Midpoint. That's exactly right. I don't know why they go together, but they do. We're going to find the midpoint of the line segment.
Isn't that just dividing all the x, y, z coordinates by 2?
Yes. What do you have to do with the x's and the y's and the z's first?
Do you find the difference between them?
Not the difference, but
Yes.
not the distance.
Their values.
No. It's the sum. Thank you, Becca. It's the sum. A midpoint is an averaging effect, right? It's like saying, what's your average exam effect, right? What you just add your 2 exams together, divide by 2. That's what midpoint does, is it adds each of the components together, divides by 2. So the segment joining the points. And the points that we have here are 3, 4, 6, and 1, 8, 0. So you guys told me that we're going to find the midpoint, eventually you told me, by adding the component y's together and dividing each of them by 2. So what would be the midpoint of this line segment? 2, 6, 3. All good? All right, closely related to the distance formula and the midpoint formula, but it's from the distance formula, but usually all taught at the same time in an algebra course, there's one other equation.
Wait, it's supposed to be 3 plus 1?
Which one?
Are we sure it's supposed to be 3 plus 1? Yes.
Mm-hmm.
You're all sure.
Yep.
But it's the midpoint, like 100%.
Right, because halfway between 3 and 1 would be 2, right? So 3 plus 1 would give me 4 divided by 2, so I have halfway between 3 and 1 is 2. This is the halfway point of each of the x, y, and z coordinates. Okay? All right. So when we talked about, when we look at the distance formula in 2 dimensions, think about what it looks like. It says d equals the square root. You've got the difference in the x value squared, the difference in the y value squared. If you squared both sides of it, what equation would that give you?
What, you squared both sides?
Mm-hmm.
So d squared equals
D squared equals,
x plus, or delta x.
uh-huh. If you had the, it's a Pythagorean theorem, or I mean, we've got some of that going on, but there's something else.
You'd end up with,
A squared plus B squared equals C squared, Pythagorean theorem.
yeah.
There's another thing that comes about from that.
It's like area around.
Oh, you're getting so close, Bryson.
It's like circumference, but it's not a circular object. Perimeter.
No.
No.
Nope. All right, I give up. It's the equation of a circle.
Oh.
Yeah, so if you square both sides of the distance formula, you end up with a version of the formula for a circle. And in 3 dimensions, a circle would become a sphere. Awesome. So next thing we're going to look at is a sphere. This is like a guessing game day. Isn't it fun? Yeah. So, no, we're not finding area and volume. We're finding an equation of a circle. And a sphere, actually. Find the equation of the sphere. And when you're doing this for circles, what happens is you need to know the center of the circle and the radius of the circle, or be able to find those two things if you're given some other pieces of information. So we're going to have the same information given here. We have the radius. In our case, we're going to do a radius of 2. And the center, and our center is going to be 3, 1, 4. So when we deal with circles, the first thing we would do is we would take, for example, x minus 3 squared. And then what would we do? Plus y minus 1 squared. And so what do you think we're going to do next? Probably the z minus 4 squared, yeah. And it would equal 2 squared or 4. All good? Yeah. Okay. But what I want to remind you of is that also you are sometimes given an equation of a sphere. In this case, we're doing sphere, but you were doing it with circles before, where it's not in that nice, neat little formula. It's all messy, right? Okay, so we're going to practice our hand at trying to separate that out with a fairly straightforward one. And we do it with completing the square. Complete the square. To write the equation in standard form. That's the form that we just put the other one in. And we're going to find the center and radius. Okay, and our starting version of this says x squared minus 2x plus y squared plus z squared minus 4z equals 0. So let's see what you guys remember about completing the square. Some of you do this kind of stuff with tutoring and everything, but not all of you, so it may have been a little bit. So,
Well, we're dealing with the square for x.
okay, so if I were dealing with the squaring for x, what would I need to complete this square?
Half of 2x.
Half of 2 and then squared, which would be 1. And in the end over here, I need to add a 1, right? To the other side of the equation. This one's actually fairly nice because there isn't a need to complete the square for y, because it is just y squared. But for z squared, what do I need to complete this part of it? Half a negative 4 squared, which would actually be a positive 4.
Wait, it's 4z?
It is 4z, yeah. It was probably in Calc 3 or my version of it when I started putting my line through the middle of my z's. So it might be something to consider. If not, be really careful on your z's because sometimes they look like 2's if you write quickly. So, and then add a 4 to the side. Okay, everybody good with that? Okay, each of those now factor nicely. So this would be x minus 1 squared plus y squared plus z minus 2 squared. Remember, that's the whole point of completing the squares. It makes them factor nicely into perfect squares, and it equals 5. So, what is the center of our sphere? 1, 0, 2, and our radius is square root of 5. Well done. Okay, so this is all three-dimensional stuff that's really not vectors at this point, agreed? But we're about to shift into doing that. These are not vectors at the moment, no. They're definitely not. But very soon. Are you ready? Yeah? Oh my goodness. All right, are you ready? Really? Ethan, are you good? Can we switch? Okay, cool. All right, we're going to do the same thing as we keep moving our way through vectors. I considered like giving you all these formulas, but I thought this is silly. I think you guys can rationalize what the next step would be in 3 dimensions from having done all of this in 2 dimensions. So I decided to go that route, and it looks like you're doing okay. So we're going to start by finding the vector and its magnitude. And we're going to do that on this problem with an initial point and a final point, or terminal point. So we have initial point, 3, 2, 0, and we have a terminal point, 4, 1, 6. So we'll start by finding our vector. So how did we find vectors when we had 2-dimensional space? We just subtracted them component-wise, right? Yeah, same thing here. So component-wise subtraction, and the reality is that we go terminal point minus initial point. They're only slightly different, of course, by negatives, but if we did that, what would we get for our vector? 1, negative 1, 6. Is everybody good with that? Okay. And then last time we talked about magnitude as well. What did we do with magnitude? Yeah, it's the distance formula, right? Or the Pythagorean theorem. That's all it is, you bet. And it works just the same way in 3 dimensions. So I'm going to have, just like I did on the last problems where I was finding distances, 1 squared plus 1 squared plus 6 squared. Remember, signs don't really matter because we're squaring. For a total of what? Square root of 38. You got it. Okay, so we're going to continue using this particular vector because we already created it. We might as well use it. So using v above. What's that?
There's a lot easier way to think about it. Because like physics, like I just know to do that, but it's like the distance.
Yeah, it's the distance formula. You got it. That's right. It's like, why do we need all the words for meaning the same thing, right? We're going to find, I'm going to let you guys do this, and we'll check to make sure everybody has the same thing. You're going to find these different scalar multiples of the vector that we already created. So you're going to find 2v, negative v, and 3/2 v. So find those 3 quantities, and then grab somebody nearby and just confirm that you have the same values. Okay, are they matching up? Seeing some nodding of heads. All right, Hannah, tell me what you got on the first one.
2 negative 2 12.
2 negative 2 12s. Does everybody have that?
I have a negative 12.
You have a negative 12.
Oh wait, no, I did it wrong earlier.
Okay. It's all right.
I'm just an idiot.
That's all right. Hey, Andrew, why don't you give us the next one, though? What'd you get the next one?
Okay, well, let me fix my.
Fair enough.
1, 1, negative 6.
Negative 1, 1, negative 6. Is that what everyone has? Fabulous. Shayna, how about you give me the third one?
I got 3 halves, negative 3 halves, and 9.
All right. And that match for everyone else, too? Fabulous. Okay. So just like when we did it in 2 dimensions, we can also add and subtract and multiply and divide with vectors, right? Multiply and divide with scalar values of vectors. So we're going to give that a try with another example with a couple of vectors. So here's our directions. We're going to be given vectors u, v, and w. So u is, because I know that some of you really like your ijk's, I minus 4j minus 2k. It's really sloppy looking. There we go. V is I minus 3j plus 4k. And then W is 2I plus j minus k. So those are our initial 3 vectors. And we're going to find the z vector, which is going to be u minus 2v plus 3w. And in some sense, ij's and k's is almost easier to work with on this than the component-wise form that we've been using on the other examples, because it starts to look a lot like just algebra with linear components. I don't mean linear algebra exactly, but algebra with linear components. So if we're thinking about it like that, we have our u vector, that's I minus 4j minus 2k. And then we have the scalar multiple of 2 times the v vector, which is I minus 3j plus 4k. And then we have the scalar multiple of 3 times the w vector, which is 2I plus j minus k. Messy, but this is a college algebra problem at this point, right? Yeah. My college algebra students are working on different things that feel a lot like this. So, multiply things out, combine like terms. Once you get to the end, see if you and your neighbor's papers match, or if you can find where one of you has been led astray. Okay, are they matching? Okay, David, what'd you get for your last step?
5i plus 5j minus 13k.
Okay, and at this point, it sounds like from Kyle, we would have to change that into component form if we wanted to put it into WebAssign, right? It was liking the other component form better. Fair enough. But is that good for everybody? Do you have those same components? Yeah? Awesome. Using this piece, because I thought, we might as well use the pieces we already have, we're going to find the magnitude of this. So, what components am I going to have? What are the values going to be in under my square root? Yeah, 5 squared, those are 25s, and 13 squared, which is 169. What's that total? $219, which isn't prime. 219 does divide by something. Do you know what it divides by?
3.
It divides by 3, but if you divide it by 3, you'll end up with, I think it's 73, and that is prime. So you can't really do anything else. You just leave it that way. Okay, continuing with the same example because we can. Do you have a question?
Unit vector, is that what we're finding?
Yes, that's exactly what we're going to find. We're going to find a unit vector. Your book does ask a couple of versions of this, so I thought we might as well try it. Find a unit vector, and the first unit vector we're going to find is in the direction of z. And then the second one is going to be in the opposite direction of z.
Mm-hmm.
So when we found unit vectors, how did we do that? Go ahead, Ethan.
I believe we divided the vector by the magnitude.
We did. We divided the vector by the magnitude.
And then for opposite direction, we just used opposite signs.
We do. Yeah, we just have to switch the signs for part B on this. And we need to rationalize as we go. This one's actually fairly nice to rationalize simply because it doesn't simplify anyway. So if we write it down, we're going to end up on this one with the vector 5 square root 219 over 219. 5 square root 219 over 219. And then negative 13 square root 219 over 219. And then how would that look different for part B? Yeah, all the signs are switched. So the first two will be negative and the last one will be positive. So negative 5 squared root 219 over 219 on x and y components. And then a positive 13 at the end. Okay, there are a couple of interesting, I don't want to call them exactly applications because application contends that you've got a lot of context involved, and these aren't quite like that. But they are extensions of the ideas that we've been working with. And they involve us talking one more time about what parallel vectors look like. So I'm going to talk a little bit about parallel vectors and then how we can use that information in a couple of different contexts. So parallel vectors are two non-zero vectors. We'll call them U and V, where there is a scalar C such that U is equal to C times V. So one of the vectors is a scalar multiple of the other one. That's what it takes for them to be parallel. Okay?
But couldn't they be parallel vectors if they had different endpoints and terminal points?
Yes. So when you find the vectors themselves, remember the vector is equivalent no matter where it's placed in the plane. So this is independent of location.
Should we have vector hats on this?
We should probably have vector hats on everything that we've been doing. That's why your book boldens them. So yes, I haven't been putting vector hats on anything, but yes, if you prefer, you can put them, and they look like this. This is one way to do them anyway. Where's the other ones? So if you would like, by all means, go for it. Yeah. Yeah, they have vector hats on them. Okay. So let's take a look at a couple of examples. First, a real straightforward question of whether they're parallel or not. Determine which vectors are parallel to Z, and we're going to consider Z to be the vector 3, 2, -5. And this is multiple choice, but only in the sense that we're just checking all of them. We're checking multiple options.
Yes.
They should all have vector hats. I know. 2, 4/3, -10/3. You guys are going to make me put them on all of them now, aren't you?
Yeah.
C is 6, 4, 10. And D is 1, -4, and 2. Okay, so we're basically doing 4 problems in one. We're trying to decide if each one of these independently is parallel to the original vector Z. Okay? So we're going to consider this and this simultaneously. And what are we looking for to make that decision?
I think B is definitely.
Yeah, we're looking for a scalar multiple. So we're looking to see if there's a number.
A is.
A is. What's the scalar multiple? Because that's how we decide. C is -2. Does that do it?
Yep.
Yeah, so if I can find a C value that when I multiply it by one vector or the other one, it doesn't even matter which one, right? That I can get the other vector. So this one works. How about B? Let's just go in order.
It's, yeah, 2/3.
Yes, C is 2/3 or 3/2, depending on which direction you want to look at it. So this one's a yes. What happens on C? No. Why not?
Because 10 is opposite.
Yeah, in fact, if the signs are not going to work, then you're done. You don't even have to look for numbers that work, right? And the signs actually don't work on D either, do they? They either need to all match the original signs or need to all switch from the original signs, so those can be answered as no's pretty quickly. So let me show you one of the ways that this is useful or can be used with an example. But you need a definition, at least a little bit of a definition first. Collinear points, you know what those are, right? What are collinear points? Yeah, these are points all on, and it can be more, I mean, 2 points are always collinear, right? So when we're talking about collinear points, we never talk about 2 points because that doesn't make any sense. So we're using 3 or more points, okay? So these are points all on the same line. And in 3 dimensions, it's helpful to do it in terms of vectors. So this can be determined by finding if the points form parallel vectors. So, let's take a look. We're going to use vectors to determine whether the points are collinear. And these are our points. 4, -2, 7, -2, 0, 3, and 7, -3, 9. And again, I find it easier to give them some names with letters. So what we need to figure out is if these form parallel vectors. Well, these are just points, so we need to create vectors, right? So let's find some vectors. So let's do vector AB. And it doesn't really matter whether we do, I mean, which pairs of ones we do. We just need to do 2 of them. We need to do AB, and we'll do AC. So if I form vector AB, what will that be? Sounds good. Okay, somebody else for me, form vector AC. All right, we're looking at A and C. Technically, you're doing C minus A because of the way that I've written my arrows, although in reality, it doesn't really matter for this question. 3,
Negative 1.
3, negative 1, and 2. You get it? That's the question. Parallel means they're scalar multiples of each other.
Yep, they
Are these scalar multiples? Okay, so what would C be? Because that's our justification. C would be negative 2. So, yes,
And C equals 1, negative 1/2.
these are collinear. Yeah, and if you went the other direction, right. Okay, I'm going to go ahead and write down the homework. There's one example that I didn't get to. So just jot yourself down a note. When you get to this question on the homework, you can skip it. I won't have the grader grade it. But it's a question about parallelograms. So when you get to the question about parallelograms, you're going to be like, parallelograms, she didn't talk about that, and you'll know which one it is. But let me give you the homework list so that the rest of them that you can do, and just mark this one out, but I don't remember which one it is on your homework.
If we're going to talk about parallelograms later, why don't we just postpone the homework?
Oh, because I've already told the grader I'm collecting it, and so that's why.
Nice try, though.
It is a nice try, yeah. And you really want to get this one done because it's long, but the questions themselves go pretty quick, right? I mean, we covered 13 questions in a 50-minute class period. That's pretty good.
Which question is the parallelogram?
I don't know. You can look it up in your book.
I can't remember. I'm ready for the next class.
So if we put these vectors into matrices and were reduced and found that they were linear independent,
Yes, they would be. That's true.
we've been fangirling over all of our linear geometry.
Oh, man.
It's all making sense now.
Wow.
It all makes so much more sense. They're not that hard.
They're not hard. They're quick. They're quick.
We'll just keep talking. There's a ton to me. Oh, man.
I told you there was a bunch. Yes.
Everything. Only 1/4 to do.
Okay. It's either 1 or 2 of them that are parallelogram questions. So if you're looking for those, it's going to be 1 or 2 that you're just going to mark out when you get there, okay? But I'm going to show you the example of it next time in class just so you can see how it works. It's not a super critical thing, but it is a very interesting application. So